Okay, so Dr. Sharath Raghvendra is currently an associate professor at Virginia Tech. He completed his bachelor's from IIIT Hyderabad. Further, he completed his PhD from Duke University before spending 2 years as a postdoc at Stanford. He has published in top-tier conferences like Fox, Stock, Soda, and SOCG. And his current research interests include designing optimal algorithms for problems related to matching and transport problems. So with this, the screen is yours.
Thank you. Yes, I think I would describe myself as one who is working a lot on matching problems these days. And what you see today is online matching. So I'm interested in this problem because it's a matching problem, not because it's an online problem. So if you guys are online folks, folks who are working explicitly on online algorithms, you probably will see a slightly different perspective from me than what you would expect from an online algorithms talk. Okay, so my topic for today is the minimum metric bipartite matching problem. Some of you may have heard of this. Let me introduce the problem first. You're given n servers in a metric space. For instance, in this example, in two-dimensional space, you're given 4 servers, and basically you're holding their locations. And the problem is that requests are arriving one at a time. And when a request arrives, you have to match it to a free server. Okay. For instance, you can have a request R1 arrive, and your online algorithm must immediately pick one of these 4 servers and match it to the servers. Say it picks S1. Second request comes in, let's say very close to S1, and now you're left with 3 servers, S2, S4, and S3, and you have to pick one of them. Your online algorithm has to pick one of these 3 servers and match it to R2, right? So you're allowed to match the server to a request only once. Okay. So S1 cannot be used, so you match S2 to R2, and now S2 is used up. So a third request comes in, R3, and you're left with 2 servers, S3 and S4. You can pick any one of them. Let's say you pick the online algorithm picks S4, and a 4th request comes in, and you pick it. So if you see the set of these blue edges form a matching of request to server, right? And the cost of the matching is simply the sum of the Euclidean distances for these edges. In general, if you're given a metric space, it would be the sum of the costs associated between those 2 locations in the metric space. We refer to this matching as the online matching. Of course, this is not optimal. Had you known all the requests in advance, matched them better. Right? You could have matched S1 to R2, S2 to R3, R4 to S4, and S3 to R1. That would be a much cheaper cost. So in general, when you're designing online algorithms, it's not possible to achieve optimal. What you're hoping to do is achieve a competitive algorithm. An algorithm which somehow minimizes this value alpha, which is simply the ratio of the online matching cost to the best optimal solution possible, the optimal match across all request sequences. Okay. So you want to make sure that you minimize alpha. So this problem was originally studied in the 90s. There was a paper by Kuller et al. And one by Kalyana Sundaram et al., which appeared around the same time. And both of them showed that there is an algorithm that was 2n minus 1 competitive. Recollect that n is the number of servers. So they showed 2n minus 1 competitive ratio. And they also showed there is some metric space where you cannot beat this. So there is a star metric, which basically for which you cannot hope to achieve better than 2n minus 1. There are other models of request generation. The one we are considering is the adversarial model, where we assume that the competitive ratio is the maximum across all request sequences. But there are other models which are slightly friendlier, like the oblivious adversary model and the random arrival model. And for these models, you can hope to do better. For instance, for the oblivious adversary, you can get log square and competitive algorithm, and for the random arrival model, you can get to which this is basically log and competitive. This is the nth harmonic number. So what if you're restricted to a geometry and you do anything better? And the best known solution for the line metric. So if you think of your metric to be simply a line, the best known was n to the 0.59. Competitive ratio is n to the 0.59. And the lower bound for this was a constant. So the known lower bound was a constant, the upper bound was n to the 0.5. And the long-standing open question back in 2016, when I actually started working on this, was can we get a constant competitive algorithm for the line metric? Recently, in 2021, it's been shown that there's a lower bound of omega of square root of log for the line metric. So you cannot hope to get a constant competitive algorithm. But nonetheless, the gap is too huge, n to the 0.59 for the line metric, as opposed to constant square root of log n at the lower. Yeah.
So can you explain the difference between the obvious model and the
So oblivious adversary model is admits randomized algorithm, and the random choices made by the algorithm is not known to the adversary. So you may pick one of these two servers with some probability, and the adversary wouldn't know which one you picked, so he cannot just try to beat you by placing the request exactly at the location of that server. Okay, so what's my goal today? I'm going to introduce a simple matching algorithm, online matching algorithm called the robust matching algorithm. And I'm going to show that it actually gives you the optimal competitive ratio of 2n minus 1, which is not surprising. It achieves, in the random arrival model, a competitive ratio of log n. And I'm going to show that it performs near optimally for every input instance. This is something that I'll expand on in a bit. So for now, just assume that it does something good for every input instance. And very specifically, I'm going to at least touch upon the fact that for the line metric, it gives you log n competitive. So you are able to improve from n to the 0.59 to log n competitive ratio. And the robust matching algorithm gives you. There's a bigger message I want to sort of convey, and maybe it's obvious to the online algorithms folks. So when I present the robust matching algorithm, underlying that is an implementation of that algorithm. That's a primal-dual implementation. I'll talk a little bit about that, but what's interesting is that implementation was the key to many of our results. We used a primal-dual method, and we assigned dual weights to these requests and servers. The dual weights helped us identify properties that led to some of the results that I mentioned. So in many ways, the implementation of these algorithms could potentially play a critical role in analysis of this algorithm. That's the message I want you to take away. In this presentation, I'll be just focusing on the robust matching algorithm and its input-sensitive analysis. So that's where I'll expand most on. The other results that I mentioned, I'll briefly talk about them, maybe a slide or two. Okay. So what do I mean by input sensitive? Maybe I describe that first. Okay. So in this problem, the very initial input you get is the set of server locations, n server locations. Right? That's what's given to you. And I'm going to define the stretch of a point set to be basically this quantity here. Like, think of all possible subsets of S such that the diameter of that subset is greater than 0. and look at the ratio, this ratio, which is the TSP, the traveling salesman tour for that subset to the diameter of that. Okay. So in this example, for instance, you have 6 points. The black edges represents the traveling salesman tour, the minimum cost tour that visits all the points, and the red edge is the diameter, which means it's the furthest pair of points, right, for this set. The ratio of these two is mu of s. Okay. I'm going to show that for any online algorithm with s as input, the competitive ratio has to be omega of mu of s. Okay. And what I mean by that is, imagine you're given s in advance, and you are designing the online algorithm specifically for s. Okay. Your only goal is, okay, this is the server given to you. I want to design an online matching algorithm for this set of servers. Then any such algorithm will have to have a competitive ratio of at least mu of s. And what I'm going to also prove on the positive side is that the matching algorithm that I'm going to talk about has a competitive ratio of mu of s log square. So it's near optimal for every input instance. Okay. So clearly our algorithm does not know the initial set of server locations. You can describe it without that. Nonetheless, it actually gives you performance that's sensitive to this. The competitive ratio is mu of s log square. Now, for a line metric, what is mu of s? If your points are on a line, the traveling salesman tour is simply twice the diameter, right? Because you just scan through them left to right and go back. And so the competitive ratio automatically becomes log square, right? Which is a big improvement from 8 to the 0.5. Okay, let's talk of the easy things first, the lower bound. Let's assume the set of server locations are given to you, and this here is the subset that maximizes the traveling salesman tour to the diameter ratio. So these are the server locations corresponding to S prime. Now, what we do is we first R1 at the location S1. Okay. The online algorithm will simply match S1 to R1. Now we also place R2 at S1. Any online algorithm is forced to assign one of the other servers. So S1 is used up. So let's say, for the sake of argument, S2 is assigned. So what the adversary will now do is place R3 exactly at the location of S2. Right? And then to serve R3, the online algorithm has to pick something else. So we can repeat this argument. And what you see is that the set of online edges actually forms a path that visits all the points. In other words, it's a traveling salesman path and not necessarily the optimal one. Therefore, the traveling salesman path of S prime or tour of S prime should be less than or equal to the cost of the online match. So the length of this path should be at most the traveling salesman. So let's look at the optimal matching. What's the optimal matching here? S1 to R1, S2 to R3. Basically, you can match with zero cost all of the requests except R2. Right? R2 will basically match to SF, the last one. And this is at most the diameter of the points. Right? So in other words, the online matching is greater than the TSP. The optimal matching is less than the diameter. So you can take the ratio here, and that's at most, or rather at least TSP by diameter, which means there's a lower bound of mu of s. Yes.
For any point set, or is it lower bound? For any point set, or is it for this particular?
So no matter what point set you choose, look at the subset of points that maximizes the TSP by diameter, take that and place and create the same construction, right? And you'll see that, okay, the online edges will form a path that spans all the points, and the offline matching, optimal matching will simply be there will be only one non-trivial edge in the offline optimal. So that has to be upper bounded. That's it. The diameter is an upper bound on that matching edge.
So it's like traveling space and path, right?
Yeah, they're within constant factor of each other. So I'm sort of being a little bit, hand wavy here. The equations are not quite accurate if you want to be critical. The traveling salesman path, if you add a direct edge between the endpoints of the path, you get a torque. So it will be at most 2 times the cost. Everything's in the big O, so I'm used to hiding the constants. Okay, so let's go to the upper bound. And what I have to do is I have to give you this simple matching algorithm to describe it to you. And then I'll give you an intuition of the analysis. It's not very difficult. The actual paper, if you read it, is very technical, but the actual intuition is not. And so I focus on the intuition. Okay, some basics of matching. This is where my expertise is, I guess. So most of you may know this, but an augmenting path in the context of matching. So here, the set of black edges is a matching, okay, that we have. And an augmenting path with respect to this set of solid black edges is really, for instance, this one, which is basically a path that alternates between non-matching and matching edges, and which starts at a free vertex and ends at a free vertex, right? And the nice part about augmenting paths is that you can augment the matching along the path, which is basically you can flip the edges. You can remove the 2 edges, the matching edges here, and add these 3 to the matching, right? And by doing so, you're increasing the cardinality of the matching by 1. So this is one way to sort of build a perfect matching. Start with an empty matching, find an augmenting path, augment the matching along. If you keep doing it, you'll end up finding the perfect match. I'm going to define something. This is very new. You wouldn't, if you haven't read my paper, you wouldn't know about this. Is the notion of T-net cost. Okay. So what is T-net cost? It's the following quantity. So if you give me an augmenting path, let's say this one, the one on the top, the T-net cost is simply look at all the edges of this path that are not in the matching, take their cost and multiply it with a factor T. T is some constant. Okay. Let's say for simplicity, think of T as 3. So multiply the cost of these edges by 3 and add them up, and then subtract the cost of all the edges that are in the matching. Okay. So simply T times the sum of all the edges that are not in the matching minus the sum of the cost of edges that are in the matching. When T is 1, this is your classical min cost matching Hungarian algorithms path, which is the net cost. It's typically called net cost by folks who do min cost matching. This is basically a modification of that. We use some parameter T. Okay, and in the context when T is 1, you can see this as simply the increase in the cost of matching due to augmentation. Okay, because these are precisely the edges that are entering the matching. These are precisely the edges that are exiting the matching. So if T is 1, this is the increase in the cost of the matching due to augmentation. Okay, so now let me present the algorithm. Before that, any? So this online algorithm maintains 2 matches. One is the online matching, of course, and another one is the offline matching. I'm going to call it the offline matching. And I'm going to denote it with this M star. So whenever you see M star, think of it as the offline matching. Offline matching's role is internal to the algorithm. It's basically helping you guide your online decisions. Okay? So the blue edges here are the offline matching edges, and the green edges are the online matching edges. And at this point, both are identical. They have the same set of edges. Now the fourth, I'm going to tell you how this fourth request is processed, and that sort of will tell you how any how the requests are processed in general. So let's say this is the fourth request that arrives. Here's what we do. The algorithm. Here's what the algorithm does. It's going to compute the minimum T net cost augmenting path from this request. Okay, let's say this one. So this here is, let's say, the minimum T net cost augmenting path. And then what we are going to do is we are going to take the two endpoints of this augmenting path. In the online matching, we're going to directly match. To be my online matching. That's the decision I make for my online matching. And the offline matching I update by simply augmenting the matching along. That's it. That's the algorithm. So every time when you get a new request, you compute the minimum T net cost augmenting path and take the two endpoints of that path, match them directly, and augment the offline matching along this. So online matching just match the endpoints directly, offline matching just augment the matching along. Okay. So that's the algorithm. Any clarifications, questions? Okay. So before we move on to analyzing this algorithm, yeah.
I guess you said TT later.
Yes. So there is a property of this algorithm that comes right after I describe this slide. That property sort of emphasizes the importance of T, and at that point I'll tell you what we fix T to. Okay. As I said, you can assume for now T is 3, if it helps. But T is this interesting parameter that has some nice behavior. It acts as this learning parameter if you want to think of it as a learning algorithm. I don't want to get into the details because I might end up confusing you more than helping you on that. But yes, we'll describe what T should be in a bit.
Can you go back to the previous slide?
Sure.
Now here we have two colors.
Right.
But in the general augmenting part, there's no notion of colors. You could end up with endpoints the same color. That won't happen.
Sorry, what colors are you talking of?
Here you're matching blue with the red.
No, so it's a bipartite. So these red points are the server, blue points are the request. And
what is the path? This is a path.
that won't happen. I think that's kind of one of the properties of augmenting paths. So, classical matching theorem says that as long as you don't have a perfect matching, you can keep computing augmenting paths. In other words, paths that start at the red point and ends at a blue point. Now, of course, there are many augmenting paths possible. So our goal is to find the one that minimizes the T net cost. So. Okay, so before we get into the properties of this algorithm or the competitive ratio, one question is how do you implement? How do you find the minimum T net cost? And one simple way to do that is to simply construct what you call the residual graph. You might have seen in your graduate algorithms class. The idea is you direct all matching edges for the offline matching, all matching edges you direct from server to request, right? And set its weight to be minus of DSR. And for all other edges which are not in the offline matching, you're going to basically direct it from R to S, the request to server, and give it a weight of T times its original cost. That's it, right? So if you do that, then for instance, this augmenting path here will basically map to a directed path in the residual graph because you're mapping all the non-matching edges from request to server and the matching edges from server to request. And then if you look at the weight of this path, all the non-matching edges have T times their weight. That's how you set the weight. It's T times the cost. So the overall weight of this path will simply be T times the weight of all the edges that are not in the matching minus the weight of the edges that are in the matching. So what we can do therefore is once we have this graph, you can run the Bellman-Ford algorithm to compute the shortest path from the newly arriving request. So just by simply running a Bellman-Ford algorithm, we can compute this path. Of course, the execution time becomes infinite. There's a smarter way to compute it, which is use the primal-dual method. And I just want to give you the intuition of what we do. I don't want to get into the details of this because it's hard for me to cover all the details. But basically what we do is, and this is what we did in my paper, we use a primal-dual method to compute the minimum T-net cost path. And how we do that is we basically set a dual weight for every request and server, and the dual weight satisfy this feasibility condition. So when T is 1, this is the classical matching dual program for the matching problem, right? So this is basically a relaxation of the classical dual problem for the matching problem. And we maintain this, and then what we do is we basically set the weight of every edge to be the slack of the edge. So what happens is slacks are always non-negative. So you can then, instead of running Bellman-Ford, you can now run Dijkstra's shortest path because you have non-negative weights. And then you can compute the minimum T-net cost augmenting path using this. So it improves your running time from N cube to N square. What I want to highlight here is that the dual weights actually play a critical role in actually analyzing this account. That was what was my, the surprise to me when I did this, that the dual weights were giving me all these nice properties. And so in some sense, the primal-dual method is not only improving the running time, it actually gives me a lot more insights into the problem. And that's the takeaway I want you to have. Okay. So now I'll answer the question of what's the role of T. Okay, so there's a critical property that helps us, a property of this algorithm that helps us analyze this algorithm. Let's look at the property. The property is that during the algorithm, what are we doing? We're computing minimum T-net cost paths. Right? If you take these, for every request, you look at the T-net cost path computed and look at its value, the T-net cost value, and add them up. This claim says that that's an upper bound on the online matching cost. You take the T-net cost value, add them up, and that gives you an upper bound on the online matching. Okay. And of course, I can simplify this. Basically, I can replace the online matching cost with this here. What is this? This is simply the length of all the augmenting paths computed by the algorithm. This offline part? Yeah, I'll come to that. So yes, so this is yes, so this is a bigger upper bound, right? It's kind of the online matching. It's an upper bound on online matching plus something, right? So it's definitely an upper bound on online matching. But yes, there's an additional parameter, and we'll talk about it a little. But first, I want you to appreciate this reduction. Basically, I can because I'm in a metric space, right? And what am I doing? My online matching edges are simply a direct connection between the endpoints of these augmenting paths. So I can as well replace the cost of the online matching with the length of all the augmenting paths. This will only be an upper bound on this, right? Because the length of the path is only going to be larger than the direct distance between the endpoints in a matrix. So therefore, I'm going to just instead prove this simple property. How do I do that? The proof turns out to be fairly simple. So let's look at every edge that enters the offline matching, right? How does an edge enter the offline matching? It's part of an augmenting path, right? So when it enters, it contributes T times its weight to the net cost. Because it's not in the matching, it contributes T times its weight. And when it exits the matching, it withdraws 1 times its weight. So every 2 times it appears, it contributes t minus 1 times its weight to the match, right? And therefore you get this quantity here. Now, to answer your question, edges of the offline matching appear odd number of times on augmented one. So we cannot pair them up as with 2 occurrences. So they contribute more to the T net cost. And what we can say is that that extra contribution is. So in total, you can prove that the sum of the T net cost is greater than or equal to T minus 1 divided by 2 times the length of the augmenting path plus T plus 1 over 2 times the cost of the augmenting. Now, when T is 1, this is meaningless because this quantity becomes 0. So this is an interesting claim only when T is greater than 1. And for our proofs, we can choose any T greater than 1. It gives us, most of the results that I mentioned will go through. So that's why I said just let's pick T to be 3. Right? Of course, the actual implementation of this algorithm and the performance, as you change T, you'll see the quality change, quality of the solutions. T appears in the constant related to the goal. Right? So when I say order of log n competitive, T shows up there. So you cannot choose T to be very large. Okay. Any questions? So I'm going to give you the intuition of the analysis. So the analysis works this way. I'm going to replace, or rather for every request, I'm going to draw 2 concentric balls. Okay. I'm going to call them the inner ball and the outer ball. And the inner ball is simply the following. It's centered at the request, and its radius is exactly equal to the T net cost, the path that you computed, divided by T. So remember, when the request arrives, when R would have arrived, our algorithm would have computed an augmenting path, right? That augmenting path's T net cost value, divide that by T, and set that as the radius of this inner ball. We know that the sum of the T net cost is an upper bound on the online matching. Therefore, the sum of the radii of these inner balls for all requests would be an upper bound on the online matching. So remember that. So sum of the radii of all the inner balls would give you an upper bound on the online matching. Then the second ball that we construct is the outer ball, and it's constructed as follows. When the new request arrives, right, when R arrives, think of the offline matching that you're maintained and take its symmetric difference with the optimal matching, the global optimal matching. What you can argue, and this is standard matching, is that that the symmetric difference contains an augmenting path. Okay, so you'll have some edges of the optimal matching and some edges of the offline matching that you're making, right, in this augmenting path. So what we're going to do is we're going to take the smallest ball that encloses this augmenting path. This is just for the analysis. We don't know what the optimal is, so we really can't construct this ball on the fly. But for the analysis, there is some optimal matching. So I can take the symmetric difference of the offline matching that I've maintained with this, with the optimal matching, and take the smallest ball that encloses this path, right? And that's what I'm going to refer to as the outer ball. The nice thing about outer ball is that it has a substantial mass of optimal edges. By construction, there are sufficiently many optimal edges that lie inside the outer ball. So our analysis strategy is simple. We want to charge the sum of the inner radii of all the requests to the optimal matching inside some carefully chosen outer ball. Okay, so we know that the sum of the radii of the inner ball is an upper bound on the online matching. So we want to charge that to the optimal matching edges in some outer ball. That's the idea. I'm going to present the analysis making two assumptions, simple assumptions. These assumptions need not hold, but I'll show you how you can eliminate these assumptions in a bit. But with these assumptions, it's very easy to see why this property is true. The competitive ratio is mu. Before I state these assumptions, first let me state that what we'll do is we'll do a simple and useful transformation. We're going to partition all the requests into log n groups. How do we do that? We basically partition them based on their inner radii. So if the inner radii are within a constant factor of each other, they go into the same partition. So this way you can partition them into log n groups. So intuitively, at least for you guys to understand the analysis, just think of these inner balls to have roughly the same radii. Because we're just going to analyze one group. And then eventually the log n term shows up in the competitive ratio because you add up across all groups. Right? So for simplicity, just assume that these inner radii are all the same for now. Outer radii, of course, can be very different. And I'm going to also additionally make these two assumptions. I'm going to assume that the requests are well separated, which means their inner radii, the inner balls are non-overlapping. So the request set is such that if you look at the inner ball, the yellow ball, they are not overlapping. I'm going to tell you how to eliminate this assumption, but for now, just make this assumption. And the second assumption I'll make is that there's at least one outer ball whose radius is proportional to the diameter of the request set. So there is some ball here, let's say this two ball, whose radii is within a constant factor of the diameter. In other words, if you expand this outer ball by a constant factor, then it covers all the requests. I'm going to make these two assumptions, and under these two assumptions, I'm going to show that the competitive ratio is mu of s. So, first of all, the sum of the inner radii is an upper bound of the online match, right? So what you can do now is, if you look at the traveling salesman tour for this point set, you'll notice because of disjointness, the sum of the radii is less than the traveling salesman tour. Why is that? Look at any edge here. Take the sum of the radii of the endpoints. That has to be less than the cost of the edge. Cost of the edge will be greater than the sum of the radii. So if you sum across all the edges, the sum of 2 times the sum of the radii will be less than the traveling salesman tour for this point. Right? So now we can say that our online matching is less than traveling salesman tour. Now, of course, from assumption 2, I know that there is a ball which has a significant fraction of online optimal matching edges. In particular, I know that the outer ball's property is that it contains, if you look at the optimal matching edges that the outer ball contains, that's at least radius of that ball divided by some constant. Okay. So in other words, the optimal matching is at least the diameter of the request site divided by some constant. So online matching is at most TSP, offline matching, optimal matching is at least the diameter divided by some constant of this request site. So therefore, the competitive ratio is TSP divided by diameter of the request. Visually very simple to see. Let me state how we remove these assumptions. Okay. I'll start by talking about assumption 2 and how to remove the assumption 2. And I'm going to use what's called the Vitali's covering lemma. if you do not know this, you would probably say you came up with it yourself. It's a pretty straightforward lemma. It has a name. And it's used quite often in real analysis. So imagine a set of balls in metric space, right? The lemma says that there is a subset of these balls that are disjoint that you can select, such that their 3 expansion encloses all the balls. For instance, in this example, if you look at these 3 gray balls, right, they're all disjoint. The 3 gray balls here, they're disjoint. And if you expand them by a factor of 3, they enclose all the balls. Right? So, and the construction is pretty simple. This is how you will do it if you want to construct this disjoint set of balls. What you do is you first take the largest radii ball in this set, and then remove all those balls that are intersecting with this. All those balls that you remove will have a smaller radii than the one that you selected. So their 3 expansion, the 3 expansion of that ball that you selected would cover all these. So the remaining balls, of course, are disjoint from the ball that you selected. So you can pick the next largest one from the remaining and continue this construction, and that will give you a set of disjoint balls whose 3 expansion covers all. I'm going to use the term subcollection to denote the selected ball and all the balls that you deleted when you selected this. Right? So when I say subcollection, think of it as the ball that was selected and all the balls that were deleted as part of when you selected this.
Anything specific about 3 or 2 based on your definition?
3 is tight. You cannot do better than 3. Especially when the balls are all of the same radii and they are just touching each other. Right? In that case, just to enclose all the balls that are touching, you have to expand them by a factor of 3. 3 is actually. So here's what we are going to do for our analysis to eliminate the second assumption. What I'm going to do is I'm going to take all the outer balls I have. Remember, the outer balls may not satisfy assumption 2. So what I'm going to do is I'm going to take all of them, apply Vitalis covering lemma, and divide my outer balls into subcollections. For every subcollection like this, there is some ball whose radius is proportional to the diameter of the request in that subcollection, because the 3 expansion covers all the balls in the subcollection. Right? So assumption 2 holds for each such subcollection. Right? So for instance, I might have the Vitalis covering lemma might have selected this ball, this one, this one, this one, and this one, and you would have deleted the rest. Right? So what I'll do is I'll basically, for all the selected balls, I look at the subcollection, the big balls that I deleted when I selected this ball, and I'm going to take those requests, and I'm going to show that for this subcollection, the sum of the inner radii divided by the optimal matching cost is PSP by diameter. And for each one of them, I'm going to do, and finally, I'm going to simply express the competitive ratio, the convex combination of each one of these. Right? And therefore, the worst case, basically I can, using this, bound the competitive ratio by mu of s. To remove assumption 1, I'm going to basically do the following. What was assumption 1? The assumption was that all the inner balls are disjoint. They may not be disjoint, in which case, if they are too close to each other, I'm going to create a single cluster. I'm going to cluster my requests depending on whether those requests are close to each other or whether they're far apart. And I'll create clusters that are disjoint. And for every cluster, I have a weight associated. Now, instead of analyzing request by request, I'm going to analyze it cluster by cluster. And thankfully, for the clusters that I create, the inner balls are disjoint. Okay. So this creates a complication. The weights that we assign to cluster creates a complication that forces me to do further refinement of my groups. Remember, groups were basically partition of requests such that two requests belong to the same group if their inner ball radii are within constant factor of each other, right? I have to further refine that and make sure that each group into subgroups such that two requests belong to the same subgroup if both the inner radii and outer radii are within constant factor. And that sort of increases the number of subgroups to log square. Okay, and then I have to, and this is all because I have to cluster the points and create, basically give them weights. Right? So that's the reason why this additional complication comes. And the total number of subgroups becomes log square n, and when we analyze it fully, we end up getting a competitive ratio of mu s log square n. So of course, for 1D, going back to the line metric, this gives me a log square and competitive algorithm. It's definitely an improvement over the previous work, but there's still a gap. And at that point, the gap was log square n versus constant. Right? Constant was the lower bound, log square n was the upper bound. So natural question that arose was, for the line metric, can we do something smarter? Can we use the specific properties of points being on a line to get even better results? And this one slide sort of gives you an overview of what we did. We basically proved that the competitive ratio of this algorithm on a line is log n, and it's tight. You cannot, like, there is an instance where this algorithm will give you exactly log n. Right? So for this algorithm, log n is tight. The way we did that was interesting. Remember the primal-dual method that I mentioned? We basically now do something more. We, for every request, we keep track of the dual weights of these requests. So the dual weights keep changing as the algorithm progresses. So what we do is we basically treat every dual weight as a ball around the request. And if the dual weight increases, the radius of the ball increases. Think of it that way. The radius of of this ball is simply the dual weight assigned to that request. If we do that in 1D, thankfully, a ball is simply an interval, right? So now what we do is we keep track of the union of these intervals. Okay? And when a new request arrives, for instance, what happens is our algorithm will basically, the primal-dual algorithm will conduct some sort of Dijkstra search and adjust the dual weights as it computes this Dijkstra search. And it may find an augmenting path, let's say, to this, right? But the dual adjustment that it did would modify the union of intervals to be this blue interval. And so the combined interval will become something very large. That's if you combine the red intervals with the blue interval, that will become, they'll start here and end here. So what we did is basically classify requests into log n groups based on the intervals they create, the length of the intervals they create. And then we showed that in each group, the cost of the online edges for that group is constant times optimal. So since there are log n groups, we were able to prove the competitive ratio to be log n. This is an oversimplification of the entire algorithm. You may have to read the paper to get all the details, but the point I want to emphasize here is that the primal-dual method played a very important role, and how the dual weights were being updated played a very important role in the analysis of this algorithm and bringing the competitive ratio down to log n. Yeah.
So previously in the general case it was log n groups and then for further log n subgroups in.
That's right. So, and that was unavoidable because of the weights. The technical issue became very important, and we had to modify Vitalis' lemma slightly, and that required uniform radii for all the upper. So that technical issue was resolved, but we found it to be fundamental to the analysis. We couldn't get rid of log square n using some other trick. So we had to specifically try this approach, like zoom in more into the dynamics of this algorithm to actually get a lock-in combination. Okay, so with this, I'm going to conclude with an open question. This is an old result, like almost 5 years now. But this came back to my, I'm actively thinking about it again because of a recent result I had on the K-server problem. If you're not familiar with the K-server problem, it's similar to matching, online matching, except every server now has infinite capacity. So when a new request arrives, a server can go serve the request and be ready to serve the next one, right? So you have, it doesn't get exhausted by serving one request. It can serve another one too, except to serve a request, it has to move to the location of the state. So, so this problem is classical. K-server is a very well-known problem. There's this notion, there's this very famous K-server conjecture on an algorithm called the work function algorithm. So here's an example of like five requests and 2 possible solutions for the K-server problem. Like you have 2 servers and 5 requests in this case. And basically, requests arrive in the order of their index. And as the request arrives, S1 decides to serve R1, R3 and R5, S2 serves R2 and R4. So you basically get for these 2 servers 2 paths. Right? And there are 2, I've shown 2 possible solutions for these 5 requests. And if you take the symmetric difference of these 2 solutions, you'll see that's an alternating trail. So for folks who may not be familiar with trail, it's simply a path which does not repeat edges. It is allowed to repeat vertices, but it does not repeat edges. It's not potentially non-simple path. So for instance, if you take R1, R3, R2, R4, R3, and R5, and you'll see that the edges alternate between blue and red. It's an alternating path, but it's not a simple path. R3 is repeated once. So you can always express the symmetric difference between any 2 valid solutions for the K-server problem as an alternating trail, 1 or more alternating trails as cycles. So what's interesting is we recently came up with an algorithm that basically give it's a faster implementation of the classical work function algorithm. And it runs in n² time per request. Interestingly, the algorithm looks quite similar to the robust matching algorithm's primal-dual method. It maintains some weights on the vertices and adjusts those weights to find these paths. Now, the natural open question, therefore, is can we use these vertex weights in some meaningful way to come up with an alternate proof for the competitive ratio of work function? And we made some progress on that, although there's no result that I can share with you yet. But we are trying to see if we can take these dual weights and analyze their behavior as the algorithm progresses and use their properties to sort of prove a competitive ratio for the K-server problem. This would be, as per my knowledge, this will be a different approach for obtaining a competitive ratio for work function algorithms. Okay, so that I'm going to conclude. Thank you.
Any questions?
No, so you're talking of the online matching problem, right? No, so you have n requests, n servers that are given to you. And when a request arrives, you have to assign a server to this request. And once it's assigned, it's exhausted. It won't be available. It's basically done. So, the other way to think of it is the server has a capacity to serve 1 request, and so that's the setting. So after you get n requests, you would have exhausted all the n servers. And what you get is an assignment of servers to requests. What is that? Which version again? It might have been. There are various variants of this algorithm. I know that there are variants. So it's a good question you ask. I've thought about this. I don't know whether there's existing literature on this. But it is quite a useful question where you have the notion of time in this whole thing, right? Like you say, for this amount of time, this location is booked. For instance, if you're thinking of parking spots, your server is really a spot and your request is really someone wanting to park a car, you would want to reserve it for some time. And so this sort of becomes a dynamic style algorithm. I'm not aware of work. There might be some, not.
Server, what is the situation? So you said it's 2K competitor and
So 2K minus 1 is a classical result by Papa Dimitrov and Kotsupias. And the lower bound is K. And the K server conjecture is whether there is a K competitive algorithm for this problem. There were people, I think, work function algorithm itself has a lower bound of only K. So there's it itself could be having an actual competitive ratio of bigger. Actually, sorry, K, right? The competitive ratio of the work function algorithm could itself be K. Yeah, that's the situation. The gap, of course, if someone wants to improve the upper bound, one has to analyze this algorithm, work function algorithm more carefully. And our hope is that the primal-dual method that we have provided, I wouldn't call it a primal-dual method because there's no dual formulation there. We do assign vertex weights on the points, and then we adjust these vertex weight to find alternating trails to move from one solution to another. And that mimics a lot of what we did in the robust matching algorithm. So the fact that we could use the dual weights to prove some things for robust matching algorithm gives me hope that maybe we can use those weights even in the context of K server to prove something. But it's all open, like the paper is published. If you guys have some bright ideas on how to use it, you can tell me. I have some observations that I find non-trivial, maybe trivial to the experts, but it is definitely giving me much more insight into the algorithm than what I was aware of before. So I find it to be a promising direction. Yeah. Not that I know of. 2K minus 1 is still the best for.
That is randomized algorithm.
Mostly in the randomized setting, yes. Randomized, there's log, polylog K. I think that's possible. But yeah.
So what is the lower bound in that case? Node?
Log K, I think. That's more or less.
There were problem. Sorry, the line metric problem that you showed. What was the lower bound? Was it root log?
The square root of log. Yes. There might be some improvement on that, but I'm not sure. I don't know of any published result that says there's an improvement on it.
The lower bound itself.
The lower bound itself. I believe it should be log n based on my experience, but I might be wrong. Maybe the square root of log n is tight.
Have you analyzed randomized algorithms for?
So that's a good question. So it's possible to sort of, instead of picking the minimum T net cost path, maybe we can take all those that are within constant factor of minimum T net cost and then pick one uniformly at random from all the augmenting paths we find, and then use that to beat the adversary and get some good competitive ratio. I tried analyzing it a little bit, but really didn't spend too much time on it. It's something that I'm happy to discuss and think about if it's worth exploring. Yeah.
So in your study, you found that the one-dimensional case was log n versus log square n for the other case. So I was wondering whether instance-dependent, so it's a metric space, so there's a dimension-dependent competitive ratio that gives this data. So you think like it's one versus.
So it's a good question. So the competitive ratio is not log square; it's mu of s log square. Mu of s is the ratio of TSP to diameter. So for a line, mu of s is 2. But if you take a two-dimensional plane, mu of s is as big as square root of s. So the competitive ratio that we proved was mu of s log square n, which means it's square root of n log square. Right? And in general, for d dimensions, the worst case ratio we get is n to the 1 minus 1 over d times log square.
Have you analyzed, let's say, for other metrics than the line metrics, in cases? Maybe, I mean, you can leave the US also. Have you sort of thought about, yeah, something like that? Other metrics, which are specific metrics.
Specific metrics, yeah. So I think the lower bound, as I said, is mu of s, and that would be square root of n for 2d into the 1 minus 1 over d for d dimension. So yes, you can get rid of the log square n, but I mean, can you get rid of the log square n is a good question to ask. I believe there might be some tricks to do that. Okay, at this point, I don't know whether we can get rid of the additional log square n, but it's an interesting question to think about. Right? It's probably not the most important one related to online matching.
The general randomized algorithm is some log n comparator. Right?
That's right. Yes, there log square n is known. Whether you can get log n for arbitrary metric is still an open question.
Rhythm has an domain question. Professor Rhythm has an domain question. Says that can this be extended to obtain some non-trivial guarantees for online non-bipartite matching? And what about the online fractional matching?
Good question. So I don't know whether one can use the same approach. Perhaps we should be able to. Many of these observations are not specific to bipartite matching. However, again, yeah, I'm not trying to see if there are properties that are very specific to bipartite graphs here that we use. Yeah, so the input sensitive analysis, it depends a lot on dual weights. So if you go into non-bipartite matching and the dual weights there, it's a lot more complex because you have to deal with these blossoms, computation of blossoms and contractions and so on. So that place, I'm not quite sure whether the analysis we have extended. Some of the basic analysis for the 2n minus 1 competitive ratio, etc., should extend even to the non-bipartite matching. And fractional matching, again, it is a non-trivial task to extend what we did to fractional matching. It perhaps could be done, but something that requires some time. Yeah.
So the problem that you suggested at the end was a non-bipartite.
It's not non-bipartite, it's a different bipartite mean cost flow problem in my opinion. It's like a variant of that. So you still have two sets, servers and requests, right? The case servers and requests. And they just only go between servers and requests. Right? So it's that sense, so it's a bipartite graph. The thing is that servers can be reused here, arbitrary number of times. So when a request arrives, you have all the case servers available to you. You can pick any one of them to serve this request. Right? And the online decision you have to make is which server will serve it. So it's still, they just go between servers and requests.
So the edge from R2 to R3 will be sort of the edge from X to 0.
That's right, yeah. You can think of it that way, yes. It's not, yeah, you're right. It's not non-bipartite matching. Matching is very specific, right? It's a one-to-one correspondence. Here you have like k paths that you're drawing out as you serve requests.
So can you define a sort of parameter like viewers for the case server column to analyze method?
Good question. So I don't know. Everything in case server becomes infinitely hard. The matchings are easier to work with. Case server problem, all the instances That's far more challenging. So I haven't tried defining it, but thinking about it as well. If there is some notion of input sensitive lower bound, and then perhaps one could prove guarantees as a function of that input sensitive. Yes. So we haven't explored. All of these are nice things to think about.
The intuition that you had for your question, was that known before or was it something?
I don't think it's terribly complicated to know why it is. Like, almost all the adversarial constructions is basically whichever server gets chosen, you put a request right there because then you cannot, you've just made a bad choice. So almost all adversarial constructions are like that. I think the surprising fact for me was that the upper bound actually for this algorithm came log square and close to being best for times mu of s.
Any other questions? I've previously studied the case where requests come from a random process.
Stochastic.
Yeah.
For matching, yes. I think there was a paper last year in ICAL, the last 2 years back, where there were if you know the two distributions, or rather if you know the request distribution and you're drawing from it, then you get better probability integration. I believe it was a log n probability integration. Whether you can get constant would be an interesting question. Second, if you have unknown distributions, you know it's coming from a distribution, but you don't know what that distribution is, can you get something better than log n? I think that's also, I believe that is also something like that.
More questions? With that, maybe we can have a speaker.
Thank you.
Thank you.